And I believe that this title is very long, but it is appropriate for this workshop because it contains graph class and logistic optimization, and it contains a width parameter. And here's the contents of my talk. So let me begin with the introduction. So probably we can skip the definition of PGUs. And yeah, this is defined as okay, so I will skip. Okay, and one of the important properties of the Treewidth is if the graph has a large Treewidth, then it has a large grid minor, and the grid minor is like this. And more precisely, this theorem says that for any integer r, there exists an integer f of r such that for any graph G, either G has a the Treewidth of G is at most f of r, or G has an r times r grid minor. Okay. And this shows the existence of such an integer f of r, but there are some beta bounds for f of r. The best known bound is 2 to the r5th, which is given by Robertson, Seaman, Thomas, and the lower bound of f of r is r squared log r. And there are some beta bounds for distributed graph classes. For example, if G is planar, then f of r is bounded by a linear function of r. And if G is bounded in a graph, f of r is bounded by linear function of r. And if G is h minor free, then it is bounded by a linear function. But this constant, which is depending on h, is a very huge constant. It contains many exponential functions and tau function of h. And as a special case of this case, if h is a complete bipartite graph k through k, then this constant is a single exponential function of k. And our results are the following. If G is h minor free, then f of r is bounded by a linear function of r, and this constant can be a single exponential function of the number of edges of h. And by using this result, we also give a bound for general case, and this bound is 2 to the r squared log n. And this result improves this result, and this general case improves this bound. And the results are based on the proof of Diestel. Okay, this is. So now let me give a formal description of our theorems. So the main theorem is that for any integer r, there exists an integer f of r, which is a single exponential function of eh times r, such that for any h minor free graph G, either the Treewidth of G is bounded by f of r, or G has an r times r grid minor. Okay, this is our main result. And if we apply this theorem in which h is r times r grid minor, if h is r times r grid, then since h has r squared edges and h has r squared boxes, by using this theorem, f of r is bounded by 2 to the r squared log r. So as a corollary of this theorem, we obtain this bound for general case. So these are our results. So in this talk, I will give a proof sketch of this main theorem. So as I said before, our proof is based on the proof of Diestel et al. So first, I will give a proof sketch of Diestel et al. So in the proof, the key lemma is the following. And this lemma says that if G has the large Treewidth, then it has either an h minor or two linkages PQ with some conditions. Here, linkage is a set of disjoint paths, and suppose that P is a set of horizontal disjoint paths like this, and Q is a set of vertical disjoint paths like this. And the first condition is that P and Q has many paths. P has P paths and Q has CP paths, many paths. And the second condition says that every horizontal path means every vertical path in Q, every vertical path. And more precisely, they show that the horizontal path can be divided into many paths, into Q paths, such that each vertical path is in, j's vertical path is contained in the j's path, and this path meets the j segment of each horizontal path. So this is the key lemma. And in their proof, they use this lemma, in which H is an R times R grid minor, and they set the parameter like this. P is R squared and C is an exponential function of R. And by applying this lemma, if we have the first conclusion, then we are done, because we have an large grid minor. And if the second conclusion is obtained, we have two linkages like this. Then in this case, they construct an R times R grid minor by using these two linkages. Okay. This is an outline of their proof. Okay. So let me explain how they construct an R times R grid minor by using these two linkages. So how to construct an R times R grid minor by using these two linkages. So roughly speaking, they choose R horizontal path and R squared vertical path with some conditions. And the condition is the following. The condition says that two adjacent horizontal paths can be connected by a path, not intersecting with the other horizontal path. So this means that, for example, vertical path like this is okay, because we can connect two adjacent paths, Pi and Pi plus 1, by using this path like this. And we can connect Pi plus 1 and Pi plus 2 like this. On the other hand, this is a bad case, because we cannot connect Pi and Pi plus 1 by using this path. If we want to connect this one with this one, the path must intersect with Pi plus 2. So this is a bad case. On the other hand, this is a good case. In this case, we have another path here, and we have two intersections here. So in this case, we can connect Pi and Pi plus 1 by using this path. Okay, so this is a good case. And if we can find R horizontal path and R squared path with this condition, then we can easily find R times R grid minor, because we can use these horizontal paths to represent R horizontal lines of this grid minor, and we use each vertical path to represent one vertical edge of a grid minor. Okay, each vertical edge can connect two adjacent paths, so we can represent this edge. Okay, and we have R squared vertical edge, so we can represent the R times R grid minor. So this is an outline of this method's proof. So now let me give an outline of our proof. So This is actually Lemma of Diestel, and we will use this lemma. And recall that they apply this lemma with these parameters. But in this case, we want to avoid this exponential function. So we use this lemma with these parameters. P is a polynomial of h times r, and C is a polynomial of h. Here, h is the number of vertices of h. Okay. And in this case, if we have the first conclusion, then everything is okay. And if we have the second conclusion, then by using these two linkages, we want to construct R time as grid minor or as H grid minor. So in the original proof, they find R times are grid minor. So in our proof, we construct a grid minor or H grid minor. Okay. This is the difference. Okay. So let me describe how to construct an H minor if we have two linkages like this. Okay. So in the original proof, they choose R horizontal path and R squared vertical path, and each vertical path is attached to R horizontal path. Okay. And in their proof, the important point is that every vertical path is attached to the common R horizontal path. Okay. So this is the reason why we need exponentially many horizontal paths. So our first idea is that we choose each path for each path independently. That is, we divide horizontal paths into many paths, and we choose each path here, and we choose another path here, and we choose another path here. So we want to find a component attached to these H paths, and what to say? We don't have to choose a component which is attached to the same path. These H paths can be different from these H paths. Okay, so this is our first idea. And since there are many vertical paths here and here and here, by using Menger's theorem, we can connect these H paths by using disjoint paths. So by combining these H paths, we can obtain H long horizontal paths. So the first idea is that we don't have to choose H paths. We can choose H paths for each path independently. So let me explain what is the attached component. So in the original proof, they use vertical paths to connect two adjacent horizontal paths, okay, Pi and Pi plus 1. But in our proof, we need to find an H minor, not a grid minor. So by using an attached component, we want to connect any two horizontal paths. Okay, so we choose H paths such that any two paths can be connected by a path. So in the original proof, this path is okay because we can connect Pi plus 1 and Pi plus 1 and Pi plus 2. But in our case, this is a bad case because we cannot connect Pi and Pi plus 2. If we want to connect them by a path, then the path must intersect with Pi plus 1. So on the other hand, this case is okay because we can connect Pi and Pi plus 2 by using this path. Okay. So roughly speaking, in the original proof, the attached component is a path. On the other hand, in our case, the attached component is a star graph with 8 leaves. So K1H. Okay. So this is our second idea. So the remaining part is okay. So what we want this structure. We want H path here, and we want attached K1H here, and we define the attached K1H and H path here, and so on. And if we find this structure, then we can easily find H minor, because we have H horizontal path, and we can use each path to represent one vertex of H, okay, because they are disjoint. And each star graph can connect two paths. So we can use these components to represent an H of H. Okay. So if we can construct such a structure, then we can find an H minor. So the remaining part is how we find the K1H minor. So our goal is to find H path and attach K1H minor like this. So to find a K1H minor, we use many vertical paths to construct one K1H minor. So because that in the original proof they use only one path to represent one attached component. But on the other hand, in our case, we use many vertical paths to represent one K1H minor. So to find a K1H minor, first we consider the graph obtained from this graph by contracting every horizontal path and we contract every connected component of G minus P like this. Then we want to find a star minor K1H in this graph, such that all leaves are on the left hand side of this graph. Okay. So to find a K1H minor in this graph, first we find many star minors in this graph like this. So this star minor has 3 leaves here, and this star minor has 3 leaves here. Okay. So we find many star minors with such that each star minor has at least 3 leaves on the left hand side. So we find many star minors. And we consider the following 2 cases separately. So in the first case, the total number of leaves is at least 3H. So in the first case, we have many star minors. So in this case, we have many star minors. And since the graph is connected, we can find a path connecting 2 star minors like this. So by using this path, we can obtain a star minor with more leaves. Each star minor has 3 leaves here, and this star minor has 4 leaves. And by repeating this procedure, we have a large star minor, and the total number of leaves is at least H, because the original one contains at least 3 H leaves. Then we can find the attached K1H and the H path. And each path is corresponding to a leaf of this minor. Okay. So in this case, we can find untouched K1H. So the second case is following. So in this case, we have only a small number of leaves. So in this case, since the original graph has many horizontal paths, we have large remaining path. So in this case, we cannot find a star minor here. So this means that these components forms a path. So that is, there is no vertex on the left-hand side with degree at least 3. So these green vertices are ordered along the path like this. So since the remaining part is very large, there exists a path of length at least r. So this is by a simple calculation. And if we have a path of length at least r, then we can find a set of paths like this. So this means that these paths, these vertices are corresponding to horizontal paths, and each vertical path must intersect with these paths. But this graph contains only these edges. So every vertical path must intersect with these vertices in this order. So we have many horizontal paths and many vertical paths, and every vertical path must intersect with these paths in the same order. So in this case, we can find that r times r grid line. So this is the second case. Okay, so here is the summary of our proof. So the first case occurs in every part, then we can find attached to K1H in every part. Then we can find this structure. So we can find an H minor by using this structure. On the other hand, if the second case occurs in some part, then we can find an R times R grid minor in that part. So this is the summary of our proof. So I will give a conclusion. So I will give I gave a proof sketch of a main theorem, and as a corollary, I have a bound for general case. And the big open problem in this area is whether this bound can be improved to a polynomial of R or not. So that's the end of my talk. Thank you.